Hello, welcome to Tennessee's at-home learning series for math. Today's lesson is for all our 7th graders out there, though all students are welcome to join in. This lesson is the 12th in our series. My name is Kayla Anderson, and I'm an 8th grade math teacher at Rocky Fork Middle School in the Rutherford County School District. I'm so excited to be your teacher for this lesson. Welcome to my virtual classroom. If you haven't seen our previous lessons, you can find them along with the optional student packet at www.tn.gov/education. If you haven't seen our previous lessons, you can still join in, but it might be more fun if you first go back and watch the other lessons since we'll be reviewing material we've discussed previously. Before we get started today, to participate fully, you will need paper, pencil, a surface to write on. Okay, let's begin. Today we're going to continue our discussion of ratios. Recall that a ratio is a comparison of two quantities using division. We can write ratios as fractions. Also remember that a unit rate is a ratio where the denominator is 1. Today we are going to add another concept to our understanding of ratios. We are going to talk about proportions. Do you know what a proportion is? Yes? Great. You will like this lesson. No? Great. That means today you get to learn something new. Let's begin by thinking about weight. What is weight? Weight is a measure of force affected by gravity. The moon's gravity is less than the Earth's gravity, so objects weigh less on the moon than on Earth. A rabbit that weighs 4.5 pounds on Earth will weigh only 75 hundredths pounds on the moon. A dog that weighs 90 pounds on Earth will weigh only 15 pounds on the moon. Think about any pattern that you see here. Using what we know, let's determine how much a cat will weigh on the moon. An average cat may weigh about 8 pounds on Earth. How much do you think it will weigh on the moon? Make a guess that you know is too high. Make a guess that you know is too low. Let's see if our answer is between your high guess and your low guess. What information are we given? Well, we know that a rabbit that weighs 4.5 pounds on Earth will weigh only 75 hundredths pounds on the moon. A dog that weighs 90 pounds on Earth will weigh only 15 pounds on the moon. We know that our cat weighs 8 pounds on Earth. So cat weighs about 8 pounds on Earth. So how can we organize this information? Well, I'm going to make a table. Is that the only way that you can organize this? Do you have to make a table? Absolutely not. You may choose to organize the information in a different way. So here is my table. Get that where you can see it. Here's my table. So I've got the weight on Earth in pounds, the weight on the moon in pounds, and then each of the animals that we're discussing. So let's fill in what we know here. So we know that the rabbit weighs 4.5 pounds on Earth and that it weighs only 75 hundredths of a pound on the moon. We know that the dog weighs 90 pounds on Earth and that it would only weigh 15 pounds on the moon. We also know that the cat we're discussing weighs 8 pounds on Earth, and we're trying to determine how much that cat would weigh on the moon. So what have we learned that might help us find the cat's weight on the moon? You are correct. Think about any pattern that you noticed. Is there a relationship between the animal's weight on Earth and the animal's weight on the moon? Do you notice anything similar about this relationship with the rabbit and the dog? Well, how can we determine a relationship? If you said find a unit rate, you are correct. How do we find a unit rate? Well, recall that a unit rate is a rate or ratio whose denominator, and remember that a denominator is the bottom number in the fraction, whose denominator is 1. So if we can make ratios and then find unit rates, we can solve this problem. Do you remember how to do that? Well, let's look at the information that we've been given in the table to set up those ratios and create unit rates. So we can set up a ratio with weight on Earth to weight on the moon. So for the rabbit, the ratio for the weight on Earth to the weight on the moon is going to be 4.5 pounds to 75 hundredths of a pound. Well, how can we make that ratio into a unit rate? Remember that we need the denominator to be 1. Well, we can use the fact that a ratio is a comparison by division. We divide both the denominator and the numerator by 75 hundredths. Remember that dividing both of them creates an equivalent ratio. Dividing both of them by the same number creates an equivalent ratio. So the denominator becomes 1. This will create a unit rate. So 4.5 divided by 75 hundredths is 6. And 75 hundredths divided by 75 hundredths is 1. So this is what our unit rate is going to look like for the rabbits. Okay, well now let's look at a ratio for the dog's weight. And remember that we are setting up a ratio of the weight on Earth to the weight on the moon. Well, how do we make a unit rate? Right, we can use division. Remember that we want the denominator to be 1. So 15 divided by 15 is going to give us a denominator of 1. If we divide the denominator by 15, we have to also divide the numerator by 15 to create an equivalent ratio. Well, 90 divided by 15 is 6. What do you notice? Right, the weight of the rabbit and the weight of the dog have the same unit rate. So what does that mean? Well, it means that an object's weight on Earth, because remember that that was the top number, is 6 times the object's weight on the moon. Or we could say that an object's weight on the moon is 1/6 of the object's weight on Earth. So how can we use that to help us determine the cat's weight on the moon? Well, remember that the cat weighs 8 pounds on Earth. So we can find 1/6 of 8, because remember that the object's weight on the moon is 1/6 of the weight on Earth. 1/6 of the weight on Earth. So if we find 1/6 of 8, we'll have the cat's weight on the moon. Well, 1/6 of 8 is 1/6 times 8. 1/6 times 8 is 8/6, or 4/3, which is the same as 1 1/3. So the cat will weigh 1 1/3 pounds on the moon. Great job. We can say that since the unit rates for the weights of the dog and the rabbit are the same, they have a proportional relationship. What does that mean? Well, that's what we are learning today. Here we go. On Sarah's favorite mobile game, she is awarded game lives when she finds gold coins. Oh, sorry, you can't even see the problem. There you go. This is what she sees when she finds gold coins. The coins are circles and the lives are hearts. What do you notice? Do you see a pattern? How many lives does Sarah get for each gold coin? You are correct. Sarah gets 3 lives for each gold coin. How can we write these as ratios? Well, let's organize our information with a table. So here's my table. We have the number of coins, the number of lives, and then a ratio of coins to lives. So for 5 coins, she gets 15 lives. For 3 coins, she gets 9 lives. For 2 coins, she gets 6 lives. Now let's set up ratios of the number of coins to the number of lives. So the number of coins to the number of lives. This will be 5/15, which can be rewritten or simplified as 1/3. This is going to be 3/9 coins to lives, which can also be rewritten as 1/3. And this will be 2 to 6, which can also be rewritten as 1/3. What do you notice? All three ratios have the same unit rate. Notice that 5/15 is equal to 3/9, which is equal to 2/6, because they're all equal to 1/3. Recall that these are called equivalent fractions. Well, this relationship is a proportional relationship. Two quantities are in a proportional relationship if all the ratios that relate the quantities are equivalent. Each ratio of coins to lives is equivalent to 1/3. The number of game lives awarded is proportional to the number of gold coins found. Next, let's think about the relationship between area of a square and the length of a side. Recall that a square has side lengths that are all equal. How do we find the area of a square? Go ahead and put this up here. Here's our squares. Remember that all four sides are equal. How do we find the area of a square? How do we find the area of the square? Right, you multiply the length times the width. Or you can find the length of the side squared. The length times the width, or the length of the side squared. We're going to compare the area and the side lengths of these three squares and then decide if the relationship between the area and the side length is proportional. So you see that one square has side lengths of 2 inches, one square has side lengths of 3 inches, and one square has side lengths of 4 inches. Let's make a table to organize this data. So here's my table. And we've got the side length, we've got the area of the square, and then we're going to create a ratio of the area to the side length. So let's record the side lengths, 2, 3, and 4, and that's in inches. Now let's record the area. So remember, the area is the side length squared, or the length times the width. So 2 squared is 4, because 2 times 2 is 4. So the length of 2 times the width of 2 is 4. 4 squared, oh, I skipped 3. 3 squared is 9, because 3 times 3 is 9, the length times the width. And 4 squared is 16, because 4 times 4 is 16. Now that we have the side length and the area, let's create a ratio of the area to the side length. An area of 4 to a side length of 2 is 4 halves, or 2. An area of 9 to a side length of 3 is 9/3, or 3. And an area of 16 with a side length of 4 is equal to 16/4, or 4. And remember that each of those can actually be written as a ratio of 2/1, 3/1, and 4/1. So what do you notice? Do you see a pattern here? Well, 2/1 is not equal to 3/1, which is not equal to 4/1. These unit rates are not equivalent. So what does this mean? Is the relationship between the area and the side length, the area and the side length, area, side length, area, side length, is that relationship proportional? Remember that relationships are proportional only if those ratios are equivalent. Since all of these unit rates are different, the ratios are not equivalent. Therefore, the relationship between area and side length is not proportional. This is not a proportional relationship, because they are not equal. Well, what about the relationship between perimeter and side length? Is that relationship proportional? Well, first let's talk about how do we find perimeter. Remember that to find perimeter, you find the sum of the side lengths. Since our shapes are squares, all the side lengths are the same. We can use 4 times the side length. Again, let's organize this in a table. This time we have a table using those same squares, but we're going to be doing perimeter here. And so this time our table says perimeter rather than area. And remember that perimeter is all the sides added up, or since all the sides are equal, 4 times the side length. So our side lengths are still 2, 3, and 4 inches. So the square that has a side length of 2 has a perimeter of 2 times 4, or 8. The square of the side length of 3 has a perimeter of 3 times 4, or 12. And the square with the side length of 4 has a perimeter of 4 times 4, which is 16. Next, let's find the ratios of perimeter to side length. So a perimeter of 8 to a side length of 2 is 8 halves, or 4. A perimeter of 12 to a side length of 3 is 12 thirds, or 4. And a perimeter of 16 to a side length of 4 is equal to 16 fourths, or 4. So what do you notice? Is the relationship between perimeter and side length proportional? Yes, it is. 8 over 2 is equal to 12 over 3, which is equal to 16 over 4, which is equal to 4 over 1. Since all of the ratios are equivalent, this is a proportional relationship. We've discussed proportional relationships. We said that there's a proportional relationship if the ratios are equivalent. Now we will talk about a proportion. A proportion is an equation that represents equal ratios. In other words, we have a proportional relationship with an unknown. Let's use this table to think about proportions. There's a proportional relationship between the number of wing beats per second for a hummingbird in flight. Have you ever seen a hummingbird when it's flying? The wings beat so fast that you can barely see them. The wing goes up, comes down, and goes back up, and this is considered a wing beat. So let's consider the data in this table. First, let's verify that this is a proportional relationship. How do we determine a proportional relationship? Right, we can find the ratio of wing beats per second and see if all of those ratios are equivalent. Well, wing beats per second, wing beats per second, wing beats per second. Well, each of these is equivalent to 80 over 1. So, because they're all equal to one another, because all of these ratios are equivalent, this is a proportional relationship. Let's use this information to determine the number of wing beats in 60 seconds. How can we do that? Well, if we know that the wings beat 80 times per second, how many times will the wings beat in 60 seconds? Well, let's set up a proportion. So 80 beats in 1 second is equal to some number of beats in 60 seconds. Remember that y is the number of beats per second. We know that there are 80 wing beats in 1 second, so there are y wing beats in 60 seconds. How do we find the value of y, which is going to be the number of wing beats? Well, we can solve this equation using strategies we already know. If we want to isolate y, what do we need to do? Well, we need to get rid of the 60. How can we do that? Well, the y is being divided by 60, so we can use inverse operations. What's the inverse of division? It's the inverse of dividing by 60. Right, multiplying by 60. So if we multiply both sides by 60, then this becomes 4,800 over 1 equals y. So what does that mean? Well, it means that the hummingbird wings will beat 4,800 times in 60 seconds. Wow, that's fast. Well, let's take a minute and reflect on all we've discussed so far today. We know that a ratio is a comparison of two quantities by division. We know that a proportional relationship exists if the ratios are equivalent. We can determine equivalency by finding unit rates and seeing if they are the same. We discussed the definition of proportion. We said that a proportion is an equation that represents equal ratios. Now let's use what we have learned to practice. Let's think back to our problem with Sarah's mobile game. Let's do a similar problem. We'll think about this problem together. Miles records the time it takes to download a variety of file types. How is the download time related to the file size? Explain. Complete the table and decide if there's a proportional relationship. Well, we've got our type of media, we've got our document here. We've got a document, a song, and a video, and this is the file size, and this is the download time. So if we set up a proportion of download time to file size, download time to file size, and download time to file size. So reducing each of these, they're all equivalent to 20. So is this a proportional relationship? How do you know? The ratios are equivalent. They all have the same unit rate. This means that the download sizes are proportional. Let's try another example. Jenny's favorite cookie recipe requires 1.5 cups of sugar to make 24 cookies. How much sugar does Jenny need to make 36 of these cookies? You try this one on your own. Well, we can think of this ratio as the amount of sugar per number of cookies. The amount of sugar per number of cookies, which looks like this. We know that this should be a proportional relationship. Otherwise, the cookies will be too sweet or not sweet enough. So we can set up a proportion. Recall that a proportion is an equation with an unknown. So if it takes 1.5 cups of sugar to make 24 cookies, how much sugar, which we're going to represent with X, will it take to make 36 cookies? Well, let's solve this equation. Remember that we can use inverse operations. Currently, X is being divided by 36. What's the inverse of dividing by 36? Right, multiplying by 36. So if we multiply both sides by 36, then we will get 54 over 24 is equal to X, and 54 over 24 is the same as 2 1/4. So this means that Jenny will need 2 1/4 cups of sugar to make 36 of her favorite cookies. Great work. Let's try one more. Aaron and Paisley sell lemonade at a school fair. The tables show the number of glasses they sold and the amount collected on 3 different days. Question A wants to know, is there a proportional relationship between the number of glasses sold and the amount collected at the 2 lemonade stands? And who charges more for a glass of lemonade? And then explain how you know. I will give you time to answer the questions. Well, let's see how you did. First, let's look at Aaron's table. If we set up a ratio of the amount collected to the number of glasses, each of those is equal to 75 cents. So there is a proportional relationship between the amount collected and the number of glasses sold for Aaron's data, since all of these are equivalent. Let's look at Paisley's table. If we set up a ratio for the amount collected to the number of glasses, they all equal 75 cents. What does this mean? It means that there is a proportional relationship between the amount collected and the number of glasses sold for Paisley's data as well. So who charges more for a glass of lemonade? Well, they both charge 75 cents. I know this because this is the unit rate, which is the price per glass. Excellent job. Great work today, 7th grade. Today we reviewed understanding proportional relationships and equivalent ratios. I hope you're seeing some connections to ratios, unit rates, and proportions. You really did a great job today. After the video, you will have some problems to practice on your own. I'm going to show you the independent practice problems now. Here they are. Or you can find them in the student practice for this lesson posted on the website www.tn.gov/education. Good luck and do your best. I enjoyed reviewing determining whether quantities are proportional by testing for equivalent ratios with you today. Thank you for inviting me into your home. I look forward to seeing you for our next Tennessee's at Home Learning Series lesson. Bye.